Title of presentation: Weighted inequalities for sub-monotone functionals. Please.
Thank you for invitation. Absolutely, when I registered, even I forgot, but only last week you remembered me, and I apologize. Somehow, last year my co-author was presented talk, and our paper even published in your proceedings this year, and now my co-author different co-authors. Last time it was different co-authors. Now my paper is joint paper with Lubošpik from Prague. I am now in Prague, but originally from Georgia. Today is holidays, must be, no? In Ukraine there is no holiday today? Session day.
No.
Okay, and okay, my talk's about weighted inequality for sub-monotone functions. Okay, and okay, I will start very short story about Hardy inequality because it's mostly connected with Hardy inequality, and all story starts from Hardy inequality. Then after this, it was generated from monotone because in fact instead of LQ on left hand side, and historically Hardy inequality, of course, beginning was no Lebesgue spaces this time, and it was only sequences, and this is following nice inequality. It is proved by Hardy. But this best constant, what is here, it is best constant. It was defined by Landau. Okay. And after this, of course, later was find integral because four of this, and this is one is discrete or sequences, and two is now named Hardy inequality, and in this case, P must be one, but in one, in sequence case, you can take P also between 0 and 1, but originally it was not considered by Hardy. And you can see this inequality in famous book of Hardy Littwood Polya, inequalities, it's second edition, but and also this historical survey paper by Kufner, Maligranda, and Persson. And you can see all history about this inequality. Okay, if you will be define this operator, Hardy operator, like average Hardy average operator, and second integral variants, because I use it small h is by Hardy for sequential capital H, it is for integral version, average operator, and later when Hardy put it, was introduced this sequence space LP, and capital LP, it's Lebesgue integral function in power P, and now you can formulate it by following this notation, and after this Hardy inequality, you can formulate it like boundaries of this operator in sequence space from small LP, and in capital continuous case from Lebesgue LP capital LP. Okay, and this story started even before Hardy because the starting point was this famous Hilbert's inequality, double sequences following this inequality. Yes, and after this, easily you can see this left hand side. You can reformulate it by the following way. Yes, this you have this equivalent of this. You can write by LP now because after this, Hardy was trying to get this inequality for LP. Can you see? Originally, Hilbert was only 2 because no LP in this time, and this is famous Hilbert inequality, and this constant is P constant. After this, Hardy tried to get LP, and he proved by this way because can you see? It's easy. This, if you write by norms, you can in inequality 4 is you can write by this 5, and can you see this Hilbert operator which is inside? You can write by sum 2 operator, which is clear that Hardy and dual, because sometimes some authors it's named dual operator or Hobson operator, and by this you can see that all integral form also same equality, and you can see. And but by this you get inequality for Hardy and dual Hardy, and by this Hardy startup interest of this. And now it is hard inequality. I will be speaking about such hard inequalities generally. And okay, now it's formulated for weights. Before it's only power weight was, and now I put in weight. Q is, in my case, positive constant, and some authors also consider negative. And in my talk also will be some negative power also. But originally this history, and historically it's by following that when P is between 0 and P less than or equal to Q, it is this by these authors, but it's not complete authors, of course, but mostly Markenhout, Bradley, Koppler, Tomašević, already are, they was before, but after Markenhout paper, it becomes very popular. There is also Marzia Rossi, when Q less than P, and Cinnamon Stepanov, these cases, yes, historically. And now conditions, Markenhout condition was this following, and now many authors is named Markenhout condition, but after this, my paper with joint authors with Alois Kupner, Persson and Vedestik. This Kupner is from Prague, Persson and Vedestik from Sweden, and with Kupner and Persson, we have find, I think 15 condition, equivalent condition of this, because different problems is different interests, and now my talk is dedicated not condition, but equivalent of inequalities. Okay. This small history about hard inequality. Now, recently, in my paper recently, which is published just now, last week, or even Monday published this paper. And now I already mentioned that there's 4 stages of this inequality, and we find very simple proofs of this inequality. It's 100-year-old inequality, and we find this simple proofs of this inequality about hard inequality. Yes. And conditions is just only, and there is no separation P and Q, these 4 cases, because this Cinnamon situation was quite complicated. It's using Alperin level function, and Marzia's and Rosie's proofs not possible to use for situation when Q less 1, because this proof is something, but somehow I modified these proofs and I find some proofs, and it is only 9 pages. You can see only 9 pages or 8 pages, in fact, paper, which is recently quoted. Proofs is very easy. Only we using Helder inequality, this following Helder inequality 7, and okay, situation you by following way, and you get this inequality, and this Helder inequality using this condition, Markenhout condition, such form, and you get this inequality. After this using Minkowski, you get inequality. This is proved. In this case, when P is Q, when Q less than P, it's complicated. We need to discover 2 situations when it is infinity, this integral is infinity, or finite, and also proves this. Okay, this I just shown that this is only this is proof, and okay, this is okay. I'm again now this hard inequality. Now I will be motivated to equivalent conditions, not condition, inequality. And next, my talk is mostly about following paper, which is also recently accepted, and this is available by these Doi numbers in sub-monotone functions. Now it's really now starting definition of these sub-monotone functions. Okay, we have this M plus, it's standard collection of all major functions defined 0 infinity, and this for positive functions, yes, and this is we have some sub-monotone property, yes. What is this? We have this following monotonicity property of this, and for constant one, we have not subadditive, not subadditive, but with constant, because there is some operator not satisfies for some, but if you add some constant, you have additive condition, and homogeneity condition is standard condition, but with some constant, because not pre-equal. And after this, typical such norms, this Lebesgue norms for any Q, and also you can supremal operator, all such average, which is in application mostly using these operators. And now I will be consider following. If we have this row, we are defined hard inequality defined by following way. Yes, right hand side this average operator and instead of weighted LQ nor or another orange or something, we are just only putting row, no symbol because functional. Most of the total is left hand side. No, right hand side, sorry, right hand side. And P is bigger than 1. Yes, and can you see? And in special case, if you choose row, this inequality, you get this inequality. Yes, you get this hard inequality. This hard inequality special case, you need to choose row such this, and we are assuming that this inequality satisfies when right hand side is finite. Yes, and we need to find, but I will be not given characterization. I will be given equivalent condition. Sometimes dual operator is used in duality theories, but in this case, you need the row must be Banach space or null. But in our case, it's not null, it's only quasi null, yes, or even not quasi null. Even just only sub-monotone property, and still we proving duality. Okay. Okay, my theorem is like we started with inequality 13, it's already mentioned, and this satisfies for any row, and if and only about parameter P and R, this is following restriction, and this is equivalent with following inequality. Can you see? 13 equivalent with 14. Okay, under this restriction of parameters, okay, row must be any parameter for every parameter from 1 infinity, and alpha must be, and can you see? And you have dual operator here, and also some small condition about boundaries in constant operator. Because about 15 you can forget this because as usually we consider trivial situation. Yes, and consider we have dual operator because it's hard average. It is dual operator. I already mentioned this by star, and if satisfies hard inequality, we have also dual operator is bounded, and we don't need duality because row it's not nor. If it's not, of course you can use so duality go. And another version of this, is this theorem in 2 was for every, but it's enough to if x is some r and alpha is between this still equivalent. Why it is r important to this to get this r right hand side? I just mentioned that. Can you see after this r is transported to here? Can you see power r and pi? If I will be taking r big and q is LQ no, I can find this big one, yes, and this cinnamon situation by this theorem I can reduce in Maziarozin case, and it is and what is this proof of this part is very easy, and as I mentioned, this cinnamon theorem was quite complicated proof after Maziar's proof, and Rosin's proof is what. By the way, Rosin was student of Mazia, PhD student of Mazia, but he not finalized his PhD. It was subject of his PhD thesis, but he not finalized that. He died radical in Caucasus Mountain, and after this, Mazia write this proofs of these theorems in his book, very famous Sobolev space book, and by this. And he named it as a result of Mazia-Rosin, and we know this result not joint paper with Mazia, but from book of Mazia book, you can see this result. And by these theorems, I can reduce to situation of cinnamon situation when Q is less than 1 in Mazia situation, and use proof of or characterization of Mazia, and without any using Halperin level function, and not difficult. And it's also not so difficult, this proof. Also, after this, in fact, when I start this inequality, okay, there's another equality concept, maybe I will be omit of that, and I will be mentioned another. Can you see this hard inequality, what is mentioned, it's equivalent with following inequality, yes? Which is exponent and logarithm, which is geometrical average or Polyakov inequality. And in fact, this interest, my interest of this inequality starts by this Polyakov inequality. Original proof was this big Opitz paper, which is quite complicated, like 30 pages paper was. After this was simplified this result by Person and Stepanov. And after this, can you see in this theorem, this Polyakov inequality, because when you take standard Lebesgue norm, LQ norm, it is Polyakov inequality. It's to get characterization, just I showed that this is without any problem, it is equal with hard inequality. And no problem to characterize it. There is no need to prove some special proof, just this inequality. And next will be asked corollary, how can we equality rewrite these theorems to formulate from Polyakov inequality. What about 7 case? Can you see now this average is negative power, yes? Can you see under fraction, yes? This inequality, some authors, they are formulating opposite direction. I formulated like this, and this is, if you look, this is weighted average of this harmonic means, yes? In fact, you can understand this inequality like boundaries of harmonic means, because we know that harmonic means is small operator when geometrical means operator, and it's less average operator. And can you see this now, this boundaries of harmonic average, which is completely non-linear. Even this geometrical is also not linear. And this harmonic operator completely non-linear. Can you see F is under the fraction. And this is our fraction, this is harmonic means inequality. This equality is standard hard inequality. Characterization of hard inequality is well known. And also we are using this power R, because it's for any R, in this 7 is for any R, but in fact, if it is true for any R, and it is, you will be get for any R. This is inequality like this. All even this last 9 conditions, we unified both of them. This geometrical means, Polyakov operator, all harmonic means, with following average. Can you see phi? If this function phi is either concave and no decreasing, or convex and no decreasing, in this case, this inequality, where is this average here, satisfied if and only if some hard inequality, what it was mentioned in beginning. Can you see this hard inequality? It's satisfied. And this function is quite general, because, but in standard case, it's even new result will be when you row, it will be Lebesgue norm, yes, or supremal norm, yes. And in this case, in this part, it is unified. This geometrical means and harmonic means inequality, you get a special add also. This is contains all averages, yes. Even more general, you can use some log or something, and yes. And this is our main theorem. After this our theorems, you can rewrite to get characterization, as I already mentioned, about Polyakov inequality. Polyakov inequality, yes? Now characterization of Polyakov inequality, yes? It's just only corollary. If you look proof, even proof of this is, okay, 9 condition, and proof is, H proof is like 5 lines, no, not more, 8 implication. And about this is just only corollary, just only 3 lines. Proof of this is 3 lines of this. And can you see, now we're starting for Polyakov inequality, this geometrical inequality, and this inequality equivalent with Hobson inequality and also Hardy inequality. Can you see this inequality simply reducing all Hardy, all Hobson, and where this also parameter R, which is allows us to not get when you, because P is, you can take any. Can you see in this case P is not necessary to be bigger than 1. In hard inequality, it's important. It must be bigger 1. Can you see R? This hard inequality or Hobson inequality, it only satisfies when R is bigger than 1, because if R is less 1, it is only trivial solution that the weight this must all 0 or operator. And can you see now this very easily, and proof of this is only 3 lines. This Polyakov inequality we reduced Hardy all dual Hardy operator, Copson operator. Why it's sometimes different? Because as I mentioned, if you are row is null, in this case you can by duality get if you characterization of Hardy and Copson, they are equivalent. But in general, quasi Banach situation, they are not equivalent, but equivalent. Yes. Okay. And next theorems will be about harmonic means. Yes. Just only such notations using and parameters positive. This inequality, which is now boundaries of harmonic means in general quasi sub-monotone operators. Yes, it is satisfied if and only if following Copson or Hardy inequality, because this dual operator, some authors is named Copson operator, but it's really dual operator of Hardy, satisfies. Yes. And if you're interested, as I mentioned, some authors, this inequality 24, I named this like harmonic inequality, but some authors, they using just this row writing right hand side and LP norms writing left hand side. In this case, will be negative. Can you see when you writing this negative, P will be negative power minus P, and this, and it will be Hardy inequality for negative powers to understand. And some like there is paper of this Kupner and co-authors. They named this name of this title of this paper. It's named Hardy inequality for negative powers, but I am named this using like boundaries of harmonic means, and I consider like this, but it is okay. It is my first paper, which is more precise second paper, which is I think no, this month was also accepted in this Revista Computesa University Computesa, and I think will be in September will be published, but it's available online. This DOI links you can online you can get. Okay, now next our results is by another our paper which is under preparation now. It's not yet even preprint, which is these ideas. What I use the Hardy, it's everywhere. Can you see positive? Yes, but now our interest is to consider monotone functions. These ideas and these proofs we can use for monotone functions. And now next theorem in this paper is under preparation. It is now this inequality. Now I am not using operator anymore, and now my interest is to somehow consider inequality 26. Yes, and now this f is no increasing function, monotone function. Okay, I consider no increasing, but you can consider no decreasing also function. And now can you see this inequality and this sub-monotone functional, yes, row, and inequality 26, it's odd if it is following inequality satisfies. Can you see instead of f, just you can use this. Can you see one way it is easy, yes, trivial, yes, from 26 follow 27 is trivial, because if you instead of f, if you put this integral, it is decreasing function, of course, but opposite you need approximation, because any decreasing function approximates, but in this case you need Fadl property of row, but we are not assuming Fadl and we are not using approximation property, and by this it is we are giving this theorem which is without any Fadl property, this row, and very general, and no approximation property row, and so many applications such because if you consider kernel operator, boundaries of kernel operator for general kernel, and you wanted to study this operator boundaries for monotone functions, usually if you study in boundaries of operators in Lorentz spaces, you have kernel, and this kernel you need to some continuous property and some Fadl property, which is we are not assuming, and you can get these equivalent theorems by this way. And after this, you have these theorems, we can now characterize 27 by following the way. Yes, now using this theorem, what is before first paper, we are considered and get that characterization of 26 equivalent with, because can you see theorems here? Most of them is operator, which is almost trivial theorems. Just only this is, I reformulate because we avoid this approximation property, because all, if you have kernel, this kernel must be approximated good kernel, and this, but we avoid the just only monotone property of this, positivity is enough. And now can you see this boundaries for monotone functions, some boundaries of Hobson operator? Yes, and also now using these theorems, and also this, and sometimes can you see it is good Hobson operator. Sometimes it's dual version. Can you see dual version? Boundaries of Hardy operator. It is very surprising to see that why it is. If you know Hardy, why Hobson? But situation is if rho is complicated operator, let's say supramal operator also involving some kernel operator. Sometimes to characterize this for this 27 more, it's more difficult, and even some situation it is unknown, but some situation this 33 is no rounded. It's easy because there is still possibility, but when using Fubini or something, there is still for another cases it's still problems this one, but some situation this 33 is more easy to find characterization when 29 or 30, no, 20, between 29 and 36 is for every row and for exit, yes, for some. It is very important, and by parameter you can this situation and this when q less 1, by this you can increase, because can you take any r is bigger and you can increase this. Okay, I have still plenty of time. Okay, and now also this you can use also this also reduce all this geometrical inequality. It's something strange. It looks like why this hard inequality reduced geometric, but opposite when you starting geometrical for decreasing function, it's you can use opposite direction all general part. It is in fact useless situation. Now I'm mentioning such comment because we are using this simple condition, but if this row satisfies such simple condition that if row harmonic function from 0 to n follows this not limiting case, because if it has some photo property, monotonicity property, it is easily possible. But we have this condition. In this case, we also as photo property automatically counts, but if you assume this trivial condition, you can remove. Yes, now if it is situation is when this infinity is this integral infinity, which is as usually case, because finite case is not so interesting. This inequality 40 equivalent with following. Can you see you can change this operator Hardy by dual operator? Can you see? Because this is decreasing operator, this is increasing operator, and without any restriction. And also you can use this parameter alpha, yes, which is any parameter alpha. It's also very good reduction theorem, but this equivalent theorem, not in general, because first theorem was without any restriction of this capital V infinity equal to infinity. But in these theorems, it's very important. Without this assumption, capital V infinity or integral from 0 to infinity, this small v, it is infinity, is very important. Here it is important. Without this transferring of, and why we write this paper, because this referee for first paper, which is already published, referee said that you can use this one. It already was known for us, but we not put because it's 20 pages first paper, and if you put these theorems also, it become 40, 50 pages, and we decided separate paper. It will be coming soon, and it will be separate paper, this equality. I think it is my last slide. Yes, thank you for your attention. It is all my talks. I think it's on time.
Thank you very much.